How do you do? Welcome back. I missed ya, and I want to talk to you about a little mathematicas. Let's get going. Unit 5, the definite integral review. We are reviewing the unit. We are not doing every single thing. We are reviewing the meat and potatoes of the whole unit, the important stuff. This is for those of you that have seen it before, and we're just going to review it right now. Now, before we go, you'll notice that this is AP Calculus, the A and the B. A and B actually represent content in calculus. A represents derivatives. Love me some derivatives, okay? B actually represents integrals, okay? And that is what we're going to focus on moving forward, okay? Half the year in calculus, you deal in derivatives, part A. And the second half of the year, you deal in integrals, part B. If you ever hear someone who is highly intelligent in mathematics and they speak about upper level mathematics and they say differential calculus, well, that's really just calculus using derivatives. And they will say integral calculus, integrations. That is integrals, what we are going to go over now. When they say that stuff and you say to yourself, man, that dude is smart, you know that. So you dudes and dudettes, you're smart as well. All right? Let's get going. All right, let's kind of reflect back on integrals and where it all started. It is really area under the curve, so we are going to try and approximate the area under the curve using something called RAM. No, it is not random access memory, all you computer tech geeks, and I am one of them because I actually have a computer science and information systems degree. I don't know why I'm teaching math, I just love numbers, I guess, but RAM in this instance stands for rectangular approximation methods, okay? So there are three that we deal with. There's LRAM, RRAM, and MRAM. LRAM stands for left rectangular approximation method. RRAM stands for right rectangular approximation method. And MRAM is mid rectangular approximation method. If I have a graph, okay, and in calculus, you know, they're not all straight lines. There's something funky like that, blah, blah, blah. If I am going to do left rectangular approximation method, I'm going to try and approximate or guess the area under this curve. I'm going to make it easy for myself, and I'm going to kind of put as many rectangles under here as possible. Take the area of a rectangle, because I know that, it's just length times width, and then I'm going to add up all the areas of those rectangles. So what's the difference between LRAM, RRAM, and MRAM? If they tell you use LRAM, that means when I make a rectangle here, I'm going to have the left point touch my function or graph right there. Boom, boom, boom. That would be LRAM, okay? And I would have a bunch of them. Then the next one, the left edge would touch. The next one, I keep on going, the left edge would touch. The next one come up here, just the left edge. It's just the left corner touches, okay? That is LRAM. By the bee, the by the boo. Now, if I were to use RRAM, I would just want the right, oh, let me do that in another color here because my function or graph is in red. I'm going to do a rectangle here. Okay, I want the right edge to touch. Okay, so the next one here, the right edge touches. The next one here, the right edge touches. The next one here, you see what I'm saying? The right edge touches. Okay, so I'd add up all those areas, and that would be my approximation. And finally, by the bee, the by the boo, the bat. What if I used MRAM? That would be the middle of the rectangle. So the middle of my rectangle would touch, okay? Then the next one, the middle right here would touch. The next one, the middle right here, boop, would touch. The next one, the middle, boop, would touch, okay? So that is really the difference between LRAM, RRAM, and MRAM. It's what part of the top of that rectangle touches, either the left corner, the right corner, or the middle. All right. Now, this down here, the more intervals or sub-intervals, or in this case, rectangles, we have underneath our graph, the more accurate our area is going to be. So, let me do this. Let me give you another visual, because that's what I do. I give you visuals, okay? Here's this. We'll do a nice curve. It goes, something like that. Now, I'm going to do this. I'm really going to try and clone right here. So we got two graphs, same thing here. I'm going to put 4 rectangles underneath this first graph here. Graph A, here's graph B. I'm going to put 4 rectangles, and I will use LRAM, okay? So if I go from here, I cut that in half, cut it in half again. That's 4 slots. So left side touches, doom. Left side touches, doom. Left side touches, left side touches. There we go, 4 rectangles. What you will notice is the area under the curve, there are certain parts of the area under the curve that I'm not counting in my rectangles. Right here, I'm highlighting these all in yellow. You see what I'm saying? And then all that I've highlighted in yellow isn't going to be in the area in my rectangles, although it is under the curve. Okay? So if I add more rectangles, then I should have a more accurate area. So instead of 4, we'll go to here 4. Here's the 4 we currently have, right? Let's do 8. Oh my God, cut these all in half. I'm going to have 8, and I'm still going to use LRAM. So, by the boo, by the boo, it's the left corner, by the boo, 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 and left corner, by the boo. All right. Now, oh, look at that. Allie Sharp is now available. Hey, Miss Sharp. Shout out to Miss Sharp. All right. Now I'm going to go here, and let's highlight all the stuff I don't have. I mean, right here, there's a little I don't have right here, a little here, a little here, a little here, maybe dot right there. I mean, look, there is a lot more area unaccounted for here than there is here. So the more rectangles or intervals or subintervals that I have, the more accurate my area is going to be when I add up all the areas of those rectangles. It still won't be precise, but it will be a lot more accurate when I use more rectangles. Okay? Yes, we can find the actual area under the curve using the process of integration, and we will get there. All right, so now that we know a little bit about this area under the curve, LRAM, RRAM, and MRAM, or now that we've reviewed and refreshed our memories, it's like drinking a shot of espresso. Now we're going to apply that to a problem. Let's take a look at this. What do we got here? Approximate the area under the curve of the function y equals 2x minus x squared using LRAM on the interval from 0 to 2. But I need to have 4 equal rectangles. So I'm going to have 4 subintervals. Okay, so let's sketch this. Well, right now I know this is a negative quadratic here. I know that's going to be opening down. It's a downward opening parabola. Okay, so first of all, let's sketch this. All right, they want it on the interval from 0 to 2. That's from when x is 0 to when x is 2. Here's where x is 0. Here's where x is 2. Half of 2 is 1. Okay, so they want 4 subintervals. So I'm going to have to cut this in half. I'm going to have to make sure that I have 4 columns here on the bottom. Okay, here's half. Then we have 1. Then we have 1 and a half, which I will call 3 halves. And then 2. Okay, that's my x-axis. All right, so now I've got to graph this. So what I'm going to do is I am going to create a table here for my points. 0, 1 half, 1, 3 halves, and 2. All right? Now, for the sake of time, you know what? Screw it. I want to do this mentally in my head. If I throw a 0 into my x's in my equation, my y would equal 0. Again, I'm throwing my x values into this equation right there. Okay? Highlighter, that way it doesn't, all my x values are going right in there. Okay? When I throw a half in there, trust me, I get 3/4. Okay? If I throw a 1 in there, I get 1 is my output. If I throw 3 halves in there, again, I will get 3/4. And if I throw a 2 in there, I will go back to 0. So I'm going to plot all these points. Okay, my high point on the y is 1, so I'll put that right here. Okay, and then I've got to go down to 0, and it looks like 3/4 is the only other, so here's a half. Let's call this right here 3/4. So I've got to plot these points. 0, 0, right there, good douche. 1/2, 3/4. Oh, look at me go, fantastic. I can count. 1, 1, 3/2 back to 3/4. And 2 comes back to 0. So yes, there's my downward opening parabola. There you go. It's good. Now, okay, I've sketched the function from 0 to 2. Okay, I've created a table for this thing right here. The only thing that I need to write on my graph or draw are my 4 equal rectangles. And I'm using LRAM, so the left edge. Okay, so I'm going to start here, this last one. It comes up, there's the left edge, comes right to our coordinate right there. Boom. This one here, my left edge, comes right up to that point, down. This one, the left edge, comes right up to that point, down. This one, it doesn't even go up at all. It is just flat. There is no area to that. So I've got to add the area of all these curves. Now, keep in mind, please, 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 please keep in mind, all right, the height of each one of these rectangles is this coordinate. Okay? That's the height. So the height of my first here is 0. The height of my next one here is 3/4. The left edge one here is 1. The height of this left edge here is 3/4. I do not use this one. I do not need this one here for LRAM. So these are all my heights, right? It's length times height, or height times width, length times width, whatever you want to say. These are all my heights or lengths. I need to multiply each one of those by the width or the height. The width is the same for each one of these. This width, this width, this width, and this width are all the same. They are all 1/2. It's a width of 1/2. So for instance, this one right here has a width of 1/2 and a height of 1. Okay? So I'm going to multiply this times 1/2, 1. Multiply my 3/4 times 1/2. My 0 times 1/2. My 3/4 times 1/2. I can do all that math, but why don't I simply add my column up and then multiply that by 1/2 just once, instead of multiplying everything individually by a half? That's a lot of work. So what I'm going to do here is I'm going to take my 1/2 and multiply that to my sum here. 0 plus 3/4 plus 1 plus 3/4. I'm basically multiplying a half to all of those now, because wouldn't I have to distribute this? I would. Okay? But instead, let me do the addition first. Okay? 3/4 and 3/4 are 6/4. 0 goes bye-bye. 1, well, that's a fraction. That's 4/4, right? So I really have 10/4. Multiply it times my half. That would give me 5/4. And that's my area. Okay? So what did we remember? Okay, if I'm using LRAM, RRAM, whatever, depends on what point I'm using for my height, my rectangle. But I always take my width. I call it W for width. I think they call it H for height in a lot of books. And I just multiply that times the sum of all my Y values. Okay, however many I need. In this case, we had 4. We had 4 of them. All right, so this is the golden rule for RAM. Don't just add up your Y's, multiply it times your width. Hey, if your width is 1, great. Anything you multiply times 1 will stay the same. In this case, our width was 1/2. Okay, the definite integral. This is how we would find the exact area under the curve. All right. Now, let me label each one of these things for you, in case you forgot. Purple. Okay, this little S symbol here is called the integrand, or the integral. I'm going to just abbreviate that. Okay, that's telling us That's the notation telling us we need to take the integration of something. And this f of x here, well, that's our function or our equation that we're going to integrate. Okay? Now, sometimes they're bounds. Okay? Sometimes we have an upper bound and a lower bound. Those will come into play later. We'll talk about those later. That's what our B and A is, upper bound and lower bound. And this d of x is called a dummy variable. After I integrate, this basically goes bye-bye, goes away. But the notation, it needs to be there. If you were to write an integration and you don't put that dx there, you can get points off. So, let's talk about the process, okay? The process, the opposite process of the power rule, of the power derivative rule, okay? First, I need to add 1 to the exponent, and then I divide by what that new exponent is. This is the exact opposite of derivative, okay? This is the exact opposite of derivative power rule. All right, not only is it the exact opposite math, it's in the opposite order. Let me explain with an example right here before we move any further. All right, just in case you forgot. If I have 5x squared, let's say f of x is 5x squared. And I want to take the derivative. Oh, I was going to do d dx. First, the exponent comes. First, I multiply by that exponent. That happens first, right? Then, I subtract 1 from that exponent, so it becomes 10x. This is the derivative. Nothing new. Integration means I'm given this, and I'm moving backward. So if I'm moving backward, shouldn't I end up with 5x squared? I should. Okay? So not only, okay, I'm going to integrate this. Okay? Just I know I should have a dx here, whatever, but I'm going to integrate this. All right? So let's just focus on the 10x for right now. I do the opposite math. I don't multiply first, then subtract 1. I'm actually going to add 1 first. It's the opposite math in the opposite order. This is 1. I add 1 first, and I got 10x squared. Then I divide by that. Okay, well, now it's the 2, so I divide by that. 2 goes into 10 5 times. There you go. Integrate, derivative. Okay, derivative, integrate. All right? Basic power rule integration. All right? Let's start to integrate, but now we have bounds. Okay? We have bounds. We have a 3 and a -1 as my bounds for this first one. 3x squared minus 2x plus 5. Let's see how we deal with these. All right. So the first thing I'm going to do is I'm going to integrate this as I normally would, okay? So I'm going to integrate this term, and that would be 3 divided by, I would get x cubed, okay? Minus x squared is when I integrate this one, plus 5x, all right? That's the integration, but I want that from 3 to -1. All I'm going to do, okay, is I am going to take this 3, and I'm going to plug it in to my function. Whatever value that is, I'm going to subtract the value of throwing a -1 into my function. Okay? So let's start this. 3, that's going to be, okay, 3 cubed minus 3 squared plus 5 times 3. Whatever value this is, okay, I just threw a 3 in there. I'm going to subtract throwing my -1 in. So I have -1 cubed minus -1 squared plus 5 times -1. Okay, so let's do this. 27 minus 9 plus 15. That would be 6. Oh my God, is that 33? That's this value. Minus. Okay, let's make sure I did that right. 42 minus 9, that's 33, all right. Okay, this is negative 1 minus a positive 1 minus 5. That's negative 7. When I subtract a negative, it's like a super plus, plus. So I end up with an answer of 40. There you go. All right? Good. Good. It's good. And it's just that simple. All right. Cosine. Ew. There's no process to doing the integration of trig. You just got to know your trig derivatives. Okay? So basically, what I've got to say to myself here, I'll do this in green. I know this is backwards from derivative. So what would I take my derivative of? So that it would give me cosine. So what function is cosine the derivative of? Well, if I have sine, the derivative is cosine. So this is derivative, and this is moving backward. That's integration. Okay? So if I integrate cosine, the answer is definitely sine. All right? So that's just knowing your rules. So it's sine of x, but I want that from 3 pi over 2 to pi over 2. So again, I'm going to throw this into sine of x first, get that value, and subtract whatever this is when I input it into sine of x. So sine of 3, 3 pi, not just 3. 3 pi over 2 minus sine of pi over 2. Okay, the sine of 270 is negative 1 minus the sine of 90, which is 1. Okay, Visca, how do you do that so fast? Because, I don't know, people do a lot of things. I just remember my sine curve. Okay, here's 1, here's negative 1, here's 0. Go 0, 90 degrees, 180, 270, and 360. I know sine is the S. Badoosh, gadoosh, 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 gadoosh. So at 90 degrees, my answer is 1. Sine of 90 is 1. At 270, my answer is negative 1. 270, 90. All right? So what is 1 minus 1? Or excuse me, negative 1 minus 1? Negative 2 is the answer. Negative 2 is the answer. So sorry. This last one here. This last one. Okay? Hint, geometry can be helpful. Remember, this is area under the curve. That would be, what I have right here is very difficult to integrate. Okay? But what does this look like on the graph? Okay? Anytime I have kind of like circles or straight lines that I can make triangles out of, just finding the general area of a shape is helpful. I'm going to graph the square root of 4 minus x squared. Okay? The square root of 4 minus x squared. Okay? And if I graph this, I kind of have this little thing here. I'm going to zoom and make this, okay, a little bit easier to see. Hit enter. Bang, bang, and hit enter. Okay, here we go. Now, you might say, this is an oval. This is only an oval. See this window? It's rectangular. Okay, this side is obviously longer than this side. I'm going to try and make this a perfect square so that the scale is the same. Meaning, okay, there we go. I don't know, that's kind of close. So that almost looks like a square. I now have this and this as close as possible as being the same side. So this doesn't look like an oval anymore, does it? That looks like half of a circle with a radius of 2. This is going to be very difficult to integrate. But integration is area under the curve. So all I really want is the area under this curve. So if I know the area of a circle, I can just take half of that, can I? Okay, the area of a circle is pi r squared. I have half of a circle here. So I want to multiply that times a half. What's my radius? My radius is 2. So that's going to be 2 squared is 4 over 2. So I got 4 over 2 pi, which is 2 pi. There you go. That's it. The area under the curve here, the answer to that is 2 pi. But, mister, I don't see pi in there at all. Okay. If you want to take 2 and multiply it times pi, don't put 3.14. Actually put 2 times pi there. That's your answer. Okay, if they want that, if they tell you what is the exact answer, you give them 2 pi. If they say what's the answer rounded to the nearest thousandth, you tell them 6.283. All right, that's the nearest thousandths. All right, never round until you get your answer. So don't round pi and don't make that 3.14. Actually use pi, round your answer. Okay? And last but not least, when we went over derivatives, okay, there was a function in the calculator called nderiv, and that could calculate the actual derivative for us. Well, lo and behold, there is a function in the calculator, function integrate, which is number 9. I hit math 8 for derivative. I hit math 9 for integration. However, the rule for derivatives was, if I said, take the derivative of 5x squared, my calculator, at least the ones we use, would not give me 10x. You need to have a value at x equals 3. Okay, that would be 10x at x equals 3. That's 10 times 3. It would give me 30. It will give me a number. It will not give me an equation, okay, or an expression. Same thing with integration. I need bounds to plug in to get a number. Okay, so let's try one of the ones that we just did, okay, using our calculator. So let's go back, and let's take a look at this first one where the answer was 40 that I have written on the left side here in purple. Let's move this out here. I'm going to go to math and pick number 9. There I go. Now, from -1 to 3, and I don't know, maybe you need to see this if you're, okay, kids, okay. From -1 to 3, if you have a smaller screen, this is helpful. And we're going to say 3x squared minus 2x plus 5. Okay, and I have to put my dummy variable of an x here. And I hit enter, and there you go, it's 40. Absolutely what we came up with. We came up with 40 right down there, 40 down there. Beautiful. But again, you have to have the numbers that you're taking the bounds of. Okay, my 3 and -1. Which leads me to something else that I probably should have mentioned right here. Okay, what happens if I don't have bounds? Okay, what happens if I don't have bounds? Let me get rid of this. And let me show you right here if I don't have bounds. I'm going to erase some stuff. Okay. Now, I'm going to get rid of these bounds because I don't have any. Boom. Let's say I'm integrating this, but I don't have the 3 or the -1. Okay, I'm just integrating this right here. So what happens? Okay, well, if I'm taking the derivative of this and I don't have a value, the x's stay there, right? I don't have a value for x. That's what I have. Well, if I don't have any bounds for my integration here, I don't have anything to put in for the x. So it stays like this with one exception. Every time I integrate something without bounds, I always put plus c. Always, always, always. What does that mean? Remember, this is the backward process of derivatives. C represents any constant, right? Integrate. What happens if I take the derivative here? Okay, the derivative of x cubed is 3x squared. The derivative of minus x squared is minus 2x. The derivative of 5x is 5. The derivative of any constant is 0. So it would go away. Which means this constant could represent any constant. The derivative, okay, of this equation in purple, x cubed minus x squared plus 5x plus 7 is still this. Plus 9 is still this, because the 9 goes to 0 when I take the derivative, right? Plus 97 is still this, because 97 goes to 0. Minus 97 is still this, okay? Because that could be any constant, because when I take the derivative of it, it goes away, okay? So it could be anything. It could be pi. It could be Euclid's number, anything crazy, a million. All right, it could be any constant. Well, what if it wasn't a constant? What if it was 0? Well, then, yeah, I could still put plus 0 here. And I would still end up with this when I take the derivative. Now, how do we say that? How do we say, okay, yeah, maybe there wasn't a constant. Or maybe there was. Maybe the constant was 0. I don't know. We always put plus c. This would be the correct answer when I'm taking the integration. All right, without bounds, I always put a plus c at the end, which means if I'm taking the integration of cosine of x without any bounds, well, what do I take the derivative of that gives me cosine? What's my rule? Well, sine of x, if there are no bounds, plus c. Always, always, always. Okay, if there are no bounds, you need that plus c. This is a great place to stop at the 31-minute mark. We're doing fantastic. Love you guys for hanging in there. I know your brains are probably sore and you're mentally exhausted, but you know, yeah, go play some shoot 'em up game and you'll be fine again. Or go on social media and be like, oh my God, my brain hurts. So smart listening to this guy talk about calculus. Ah, that would be funny. Okay. Hey, ring that bell, baby. Hit the like button. Do whatever you do. Share. Ask me a question. Leave a comment. I'm here. I'm here for you. Kind of like a therapist, a math therapist. All right. Good luck. I'll see you for part 2 coming up shortly.